Okay, so to help out with the lab calculations, for question number 1 on the back, where we have to correct for the difference in water levels, these two pictures. Both of these, the pressure outside of the tube, so the air surrounding it, and the pressure inside the tube are the exact same. That's why the water level stops moving. Now, one of these volumes of air, though, one of the gases, is compressed. Okay, and that's because the air pressure on the outside, its volume is able to actually force water up into the tube with its pressure in order to be able to equalize things. Okay, and that's what happened to us in our lab. We ended up with water in the tube above the water level in the beaker. Okay, so we have this difference in heights. And what's happening there is that while the pressure of our gas inside the tube is equal to the pressure on the outside, it's not the same, because really those molecules, if they were in standard pressure and allowed to expand to their ideal size, they would expand further than they are. They're compressed right now. So really the pressure of that gas is weaker than the pressure of the gas in the air, and we're able to get them to become equal because there's that water in the tube that compressed the gas down. So ideally, in a lab like this, you'd sit there and you'd have the same water level in the tube as the beaker. But that's really hard to make actually happen. You have to have a really, your tubes you have to be able to measure at that level, and the measuring marks on our tubes are above the water level. So what we need to do is account for that extra height. That extra height, it's like a barometer. The pressure on the outside is pushing the water up. Okay? Now, it's water, not mercury, so we need to adjust our measurement, because right now you have a number in millimeters on the front side. Okay? For in my lab, I had a much smaller piece of zinc, so I had a lot more water in my tube. I ended up having 700 millimeters of water height. Okay? Now, to convert that to mercury, okay, so that's 700 millimeters of water was raised, I have to do a conversion. For every millimeter of mercury, so for the force that can lift 1 millimeter of mercury, that same force can lift 13.6 millimeters of water. Okay, so those are equivalent to each other. So to convert this from millimeters of water to millimeters of mercury, I put the 13.6 millimeters of water, okay, with the 1 millimeter mercury on top. My millimeters of water cancel out, and I divide by that to find out the pressure that really is only there because the water's in the tube, not created by my gas. So for me, when I calculate that out, that gives me 51.47 millimeters of mercury. Okay. Now, another thing that we have to correct for is the difference of water. So that's what we need to subtract for the difference of water levels, but we also need to subtract the water vapor. That's where that chart where the pressure of water vapor by temperature comes in handy. When I did it in the classroom, there weren't any bodies in the room, so my temperature was 22 degrees Celsius. Depending on which class you're from, your temperature may be different than that. But round your temperature to the nearest whole number and then use that chart. So for me, that was 19.8 millimeters of mercury. Okay, so I know these two numbers I have to subtract from my total pressure. Okay, and your total pressure is going to be the 759.7 millimeters of mercury that we had at that point in time. Okay, so subtract these from your total pressure. Your total pressure, or that's going to be equal to the room pressure. And that'll give you your actual gas pressure based on accounting for the water vapor, so your actual hydrogen gas pressure. So it's going to remove the water vapor and it's going to remove the inflation caused by the water being in the tube. So for question number 2, determining the molar volume of your dry gas at STP. Okay, so there's an equation to do this that we haven't learned yet, so I'm just going to show you how to set up your numbers. Okay, so you're going to have your volume on the outside. To adjust for temperature, okay, you need your standard temperature and pressure in Kelvin. Okay, so in this case, 273. And then this is going to be the room temp in Kelvin on the bottom. And then the next step, we are accounting for fixing standard temperature and pressure. Okay. And then on top, you're going to have your pressure from number 1, the one that has been adjusted for water vapor and the difference in water levels. And then on the bottom, your STP pressure. And we're going to stick to millimeters of mercury so it works with all of our other numbers. Okay. So that should be 760. If you plug in your numbers this way, you will get your volume adjusted for what it should be if we did this at 0 degrees Celsius and 1 ATM. Okay? Which we didn't do because we couldn't get the pressure inside the tube of just our gas to be the room pressure. And there's also the fact that we weren't doing it at freezing. Okay? So if you set up the numbers like this and then do the math, you'll be fine. The rest of the lab, okay, write out your balanced equation. Okay? Keep in mind when you combine magnesium and chlorine, you need to account for their charges. Hydrogen is a diatomic element. All right. So question 4 is a stoichiometry problem, but you're stopping at moles. You don't need to convert it back to mass. And then from question 5, set up a ratio. Okay. For percent error, it's your true value minus your experimental value over your true value times 100. And then question 7 will require a full stoichiometry problem. Okay, so you do have homework tonight which walks you through some stoichiometry stuff, so if you're struggling with that, I would say before moving on to question 4 and on, you might want to watch that video first.